All right. So mass, weight, density, and relative density. I said mass is the amount of particles a matter contains.
This an object contains.
Object. You know when we say matter, what's matter?
Matter is mass.
Matter.
Everything has
Matter is what?
solid, liquid, and gas.
Yes, solid, liquid, and gas. Anything that has mass and occupies space, or anything that has weight and occupies space. A matter. You are a matter. Any object is a matter. So when we say a matter, we're talking about object. You know, are you listening to me? Why we don't use the word object? If I say object, you may not think of air as an object. Did you get that?
Yeah.
But air is a matter. So anything, when we say matter, we mean anything at all that has particles. Anything that has particles has mass. The mass might be very small or very big. So the amount of particles a matter contains is a measure of its mass. Let me complete. Is a measure of its mass. All right, of course, you know, mass is a basic quantity, isn't it? Mass is a basic quantity. Mass is a basic quantity measured in kg, in kilograms, with a unit, with an instrument, or maybe you could just say with a beam balance, for instance. A beam balance
Scale.
or a scale, but it's better to use, say, beam balance. All right, that's about mass. Now, what's weight? Weight itself is a force. Weight is the gravitational force or gravitational pull. Pull of the earth on an object. The gravitational pull of the earth on an object is the weight of that object. So weight is a force because pull is about force. Right? You see, when you have an object, if you hold an object like this, are you listening to me? You hold an object like this and then you release it, what happens?
What do you say?
When you hold an object like this and you release it, what happens?
It falls.
It falls because the earth pulls it back to itself. Right?
Yeah.
So the pull of the earth on an object is the weight of that object. For some objects, the pull is stronger. For others, the pull is smaller. For instance, if you have a feather, are you listening to me? Can I detach this? Okay, yeah, that's cool. That's where we are. If you have a feather, the pull will not be as big as the pull that will be experienced with a piece of iron, isn't it? So the one that has a greater pull has a greater weight. We're on page 6 of 6. So that's fine, right?
Yeah.
Okay, weight is the gravitational pull of the earth on an object. So it's a force of gravity. You know the relationship between weight and mass? Relationship between weight and mass. Yes, what's the relationship between weight and mass?
Mass.
Okay, I'm listening.
They're both measured in kilograms.
Well, I mean the mathematical relationship. Weight is actually mass times gravitational field strength.
I love to say
Mass times gravitational field
what's weight measured? Is it not
strength.
kilograms?
Oh, I didn't remember to mention that. Weight is measured in what? Weight is a force, so it should be measured in what? Weight is a force now. Weight is measured in Newton because it's a force.
Yeah.
Forces are measured in Newton. Weight is measured in Newton. N, because it's a force. What did I say is the relationship between weight and mass?
Weight is equals to mass times
Gravitational
field strength.
All right. Mass times gravitational field strength. Now, gravitational field strength on Earth is about 9.81, or you can use 10 approximately. On Earth, gravitational field strength depends on the mass of the planet. Did you get that?
Yeah.
A bigger planet has a bigger gravitational field strength. That means the object will have a bigger weight. Let me explain that to you. Think of someone on Earth. Somebody is on Earth. Another is on the moon. The gravitational field strength on Earth, let me call it G Earth, G subscript E, is about 9.81 meter per second squared, or Newton per kilogram. Yes, I'm listening.
Why need this topic? No, I know, but then like they haven't taught us this.
Are you sure?
Yeah.
You desperately need it.
Earth is what
Like you really need it. Gravitational field strength on Earth is 9.81 Newton per kilograms. The one on the moon is 1/6 of it. Can you press 1/6 of 9.81? That's 9.81 times 1/6, or divided by 6. I need you to do that very quickly.
Me?
9.81 divided by 1/6. Let me show you. 9.81 divided by 6. That's times 1/6. That's about 1.635.
It's not times 1/6, so
That is divided by 6. That's what I mean. What did I get there?
1.635.
So the G on the moon is 1.635 Newton per kilogram. And I said weight is equal to mass times this gravitational field strength. What's your mass? When was the last time you took your mass?
What's this month? June.
What was your mass?
Like 50 or 50
50 what?
kilograms.
Good, 50 kilograms. Because when you mention a quantity in physics or science generally, you have to indicate the unit. So 50 kilograms. So your mass, 50 kilograms. On Earth, what would be your weight?
My mass times 50 times 9.8.
All right. So on Earth, your weight on Earth will be 50 times 9.81, or approximately 50 times 10. That gives about 500. But this one will give 400 and something. Give me the answer.
You already got it, your approximate.
50 times 9.81. 400 and what?
90.5.
490. Let's just say 491 Newton. That's a unit of weight, right?
Yeah.
491 Newton. Now on the moon, what will be your weight?
My weight would be 50 times 1.635.
635.
That's 81.75.
That gives 81.75. Let's just say 82.
Yeah, baby.
82 Newton. So what did you notice?
The one on the Earth.
Which one on the Earth? Your weight on Earth, 491 Newton, is bigger than your weight on the moon.
How about
Even with the same mass. Mass stays the same. Mass stays what?
the same?
But weight changes. Why does the weight change? Because of the value of the gravitational field strength.
Ouch.
Is that understood?
Yeah.
All right, mass stays the same, but gravitational field strength changes. In fact, when you get to planets that have bigger masses, you also have bigger gravitational field strength. What's the the most massive planet?
I know it's true.
So
Jupiter.
Jupiter, yeah. Jupiter has the highest mass. That means, will you weigh more on Jupiter or on Earth?
Jupiter.
You weigh more on Jupiter. Several times your weight on Jupiter. Walking on Jupiter would be a very terrible thing, because to lift your leg would be so difficult. You know, lifting your leg means you have to overcome the weight of your leg, or the pull of the earth on your leg. So you probably have to be really dragging your leg to be able to lift it. If at all your head can even stay on your head, on your neck, because your head will also be dragged to the ground. All right. We call that gravitational field strength. You see, I said Newton per kilogram. 9.81 Newton per kilogram. What's the implication? It means 1 kilogram weighs 9.81. Right? 1 kilogram weighs what? Because if I say 9.81 Newton per kilogram, that means 1 kilogram has this weight. By the way, this 9.81 Newton per kilogram is also called acceleration due to gravity.
So I feel like doing that.
All right.
Why?
Please concentrate. It's also acceleration due to gravity. Mass times acceleration due to gravity is the same thing. G is also called acceleration due to gravity, okay?
Yeah.
So mass times acceleration due to gravity. Due to gravity. Acceleration due to gravity. In fact, the general formula is this. Let me write it in W. What can I use? W is equal to mg. W is equal to mg. All right, we're making progress. On the next page, I want to just say some things about the difference between mass and weight. You know, what do you think are the differences between mass and weight? Can you mention that? I'm asking you. The difference between mass and weight.
Mass.
Let me see what's
The difference between mass and weight.
the difference.
Yes.
Let me see. Mass is a basic quantity, while weight is a force.
Excellent. Mass is a basic quantity. In fact, weight is a derived quantity because it is derived from mass and g.
Yeah.
That's one difference.
Mass is measured in kilograms.
And weight, while weight, mass is measured in kilograms, while weight is measured in newtons. So it's a difference. What other difference? We don't need to write that separately. That has already been captured. Which other one?
Okay.
Now you said mass is the quantity of matter or particles in a matter. That's for mass.
Yeah.
While
While
weight
weight
is
is
a
the
force
force.
or pull of the earth, the
Yeah.
gravitational pull of the earth on an object. Did you notice that mass stays the same irrespective of where you are? If you
Yeah.
are on the moon, you still have the same mass. What for you that has a mass of 50 kilograms is the same mass you have on the moon now, isn't it?
Yeah.
But is your weight always the same everywhere?
Varies.
So mass stays the same no matter where you are, but weight changes. Did you get that?
Yeah.
Weight changes. Why does weight change?
Because it's not fixed.
Why does weight change? Why does weight change?
This.
Because gravitational field strength is different. In fact, weight is determined by the gravitational field strength and the mass. So once the gravitational field strength changes, even if the mass is still the same, 50-50, 50 kg, 50 kg. But once the gravitational field strength changes, like on Earth 9.81, but on the moon 1.635, the weight will also change. For instance, on Earth it is 491, while on the moon it's 82 Newton and Newton. Okay? So please always remember the fact that mass stays the same, irrespective of where you are. The weight does what? Changes.
Changes.
I could ask you a simple question like this. Are you ready for that?
Yeah.
All right, then you are ready. So let's see. All right,
The class one.
let's call it a simple exercise. Did I mention that mass stays the same weight while weight changes? Okay, please let me just note it down here. I think I need to zoom in so that we can capture that. Note, mass always stays the same, but weight changes.
Happy to join.
But weight changes.
Too late.
Changes. Mass always stays the same, but weight changes. All right, look at this exercise. So the question says, the weight of an object on the moon where the gravitational field strength is 1.635 is 13.08. Find the weight of the same object on Earth. By the way, I should include the gravitational field strength on Earth, isn't it? This
Yeah.
question will always, anytime you're given this kind of question, they will give you G on Earth. G on Earth, GE, is 9.81 kilogram per Newton. Newton per kilogram. Newton per kilogram. So you used simple proportion and you cross multiplied.
Yeah.
But you see, you can also work it out like this. Assuming you were asked to find the mass, you can find the mass of the object on the moon. So this is solution. What's the mass of the object on the moon?
13.08.
13.08 is the weight.
Oh, the mass.
So what's the mass of the object on the moon?
1.
Remember, weight is equal to mass times G. M times G. So how do you find M? If W is mg, what's M?
GW.
Are you sure? If W is equal to mg, make M the set of formula. That should be W over G now, is it not?
Yeah, I said
Alright, so W is equal to mg. So M is equal to W over G. But if you can even write out all those things without even having to, and you get the answer. So for instance, what's the weight here? 13.08. So you have 13.08. We have 13.08 in place of the weight. It's equal to, what's the M? It's the mass we're looking for, isn't it?
Yeah.
I just call it M. M times what? G. And what's G? Times G on Earth now. No, G on the moon, because it's the weight I stated is the weight on the moon.
1.635.
So 1.635. 1.635. 1.635. So how do we find M? It's like saying 13 divided by what?
1.635.
Excellent. So M is simply 1 point down divided by 1.635. So M is 13.08 divided by 1.635.
Is that the answer?
That's mass. We're just looking for the mass.
Oh.
What's the mass now?
It's
8 kilograms, right? So this is the mass on Earth. Or that's the mass on the moon. And also the mass on Earth, because the mass doesn't change anyway, is it not?
yeah.
What's the mass on the moon again?
1.635.
So mass, whether on Earth or on the moon, is 9.8. I said, what's the mass?
It's the same as 8.
8 kilograms, whether on the moon or the Earth. So what do you think would be the weight on Earth now?
Is literally given.
Are you sure? Weight on Earth.
Say it now.
Weight, what you are showing me is the gravitational field strength on Earth. What will be the weight on Earth?
So what's what we're looking for?
That's what we're looking for. How do we find it? The mass is given as 8 kg. We're looking for weight. Have you forgotten that weight is equal to mass times g? Weight is equal to what?
Mass times G.
What's the mass?
8 kilo.
What's the g?
9.8.
So the weight will simply be 8 for the mass, times g on it, 9.81, and that gives us what? You see, remember the formula for density?
Mass.
Yes, density is what? Density is mass over volume. Can you see that? We normally use the symbol rho for density, but it's not really important. You don't have to use it. Excuse me. So density is mass over volume, right? So what will mass be? If density is mass over volume, what would mass be?
Mass is going to be equals to density is equals to mass over volume.
Yeah, or you can say density is equal to mass per unit volume. Mathematically, density is mass over volume. So what will mass be?
Density over volume.
Are you sure?
Mass over volume.
I said, what will mass be? This mass. What will this mass be?
Density times volume.
Density times volume, because both of them are all down. What will volume be? So first of all, mass is density times volume, right?
Yeah.
And volume is what?
Mass over density.
Mass over density. What did you say density is?
Mass over volume.
Density is mass over volume. Okay, so take note of that. So density is mass per unit volume. What do you think should be the SI unit of density?
I need I'm not sure.
Anytime you're looking for the unit of a quantity, look at the formula. Mass over volume. So it will be unit of mass
kg
per unit of volume.
I mean G per dm cube.
No, the unit of mass is kg.
Okay.
So kg per, what's the SI unit of volume? cm. No, meter cube. Meter cube. Per meter cube. Per meter cube. Right? SI unit of density is kilogram per meter cube. Other units, you can have other units are gram per centimeter cube, etc. For an example, the density of water, e.g., the density of water. The density of what?
Water
Is 1000 kilograms per meter cube. What I said the density of water is
1000 kilograms
per meter cube. All right. If you want to measure the density of a substance, what will you do?
mass over volume.
You just record the mass. What instrument can you use to record the mass?
Beam balance.
Now, if it is a regular object, an object with a regular shape, how will you measure the volume? You can measure the dimensions, isn't it?
Yeah.
And calculate the volume. For instance, if this is a block, piece of block like this. You know, and we have the dimensions as 5 centimeter, 4 centimeters, and 3 centimeters. And then we have the mass to be, the mass of this thing is 240 grams. What will it be is density? The mass is 240 grams. What will be its density?
240 times.
Remember, density is mass over volume.
Yeah, I know. 240 over 60.
Mass over volume will be, mass is 240 divided by the volume.
That's 60.
How do you get the volume? 5 times 4 times 3, isn't it?
Yeah.
The dimensions. So 5 times 4.
Yeah, that's 60.
Times 3. That gives it. So that's 240 over 60. The density is 4 kilograms per meter cube, right?
Yeah.
All right. 240 divided by 60 is it 4? Yes, it is. You will notice that if the volume increases, think about it. Are you ready?
Yeah.
If the volume increases, like if this thing expands, like a balloon expands, same mass. So what's the mass, by the way? 240. But if the volume increases, what do you think will happen to the density?
Obviously, it will increase.
Check it again. The volume, this volume, increases. If the volume increases, what happens to the density? See, no, look at it now. Listen up. I need you to. I want you to see it. What's the volume here?
60.
The same mass, 240 divided by 60, gave us 4, right?
Yeah.
Assuming the volume increases to 80, check what the density will now be with the same mass. So, if the volume increases to what? 80. So, what will you do? Is it not 240 over 80 now? Check it with the calculator and see how it affects the density. 240 over 80, see how it affects 3. So, what does that tell you? If volume increases, what happens to density?
It decreases.
Density decreases. Did you see that?
Yeah.
Alright, so for a constant mass, if volume increases, density decreases. Let's write it down. For a constant mass, when volume increases, density decreases. You know, when we did this, when we found the density of Angela, though of course that's not really a big issue. When we found the density of this object, we wrote 4 kilograms per. Yes, but I just corrected something. 4 grams. We actually wrote initially 4 kilograms per meter cube, but it should be 4 grams per centimeter cube because this is in grams.
Yes,
and the units are in centimeters, so it should have been 4 grams per centimeter cube. But I mistakenly wrote, check what you wrote.
I was copying from you.
So the unit should be 4 grams per centimeter cube. You use the units that are given in the measurement. Okay? So this is how to find the density of liquids and irregular objects. What do you use to measure the volume of a liquid? Measuring cylinder. Okay, with the measuring cylinder you can find the volume of a liquid. For instance, let's look at this liquid in this cylinder. Zoom it in. You may need to zoom it in. What's the volume?
Let me see.
That's the volume before dropping the irregular solid. But if you remember what I told you about reading a measuring cylinder or graduated scales, what are the things I say you must do?
You should do something to avoid parallax due to error.
You have to read at eye level. You can see it at eye level. And then you also read the lower meniscus, isn't it?
Yeah.
So you read the lower meniscus. What's the volume?
The volume is...
Before we dropped this stone.
47.
47, 48, 49, 50. Okay, the volume is 47 units.
47
centimeter cube. This is in centimeter cube. Because anytime you take a measurement, you have to indicate the unit. The unit will always be written on the instrument. So it's cm cube. So this is 47 cm cube.
Yeah.
47 cm cube. Do we agree?
Yeah.
Now, if you drop the irregular object, that was before we dropped the irregular object, just the liquid itself. We drop the irregular object and then the volume becomes what now?
59 centimeter.
If you zoom in properly, you can see it, just to confirm. No, I should rather zoom in, not zoom out. 47 cm cube here. That is before we drop the irregular object. Now, after we drop the irregular object, the volume has risen to, what's the new volume now?
59.
59 cm cube. So what's the volume of the object that we dropped? Remember, this is in cm cube. What do you think is the volume of this object, this irregular object?
12.
How did you get that?
Subtraction.
Good. So volume of the irregular object will now be volume of the solid, volume of irregular solid will be volume after dropping it into the water minus volume before, which is simply 59 minus 47, which is 12 cm cube. What's its mass?
39.21.
Remember, mass of irregular objects. Okay, what's its mass? 39.21 grams. So what will be its density?
Mass over...
You know, density
volume.
is equal to mass over volume, right?
Yeah.
Which is equal to what's the mass?
Mass is
39.21
grams.
over 12.
Yeah.
And what does that give us? Your calculator.
39.21 divided by 12. 3.2675.
3.27
Yeah, 3.27.
grams. You can even use 3.3 because this one is in two significant figures. Because this is in two significant figures. Look at this. The volume is in two significant figures, right?
Mm-hmm.
The mass is in four significant figures. So the answer we get by calculation should also be to the lowest. What's the lowest significant figure?
2.
2. This is in 2. Even though this is in 4, the answer we get should be to the lowest significant figure. So it should be to two significant figures. So if 3.27 means we should write 3.3, isn't it?
Yeah.
Did you get that?
Yeah.
3.3 unit. What should be the unit?
cm cube.
No. What should be the unit?
But
What should be the unit of what we just got now?
G cm cube.
Do you mean G slash cm cube?
Yeah.
Because it is division, it's about division. The unit of the one up per, that is over the unit of the one down. So that should be gram per cm cube. What did I tell you is the density of water? Do you remember? 1000 kilogram per meter cube.
Yeah.
Now this 1000 kilogram per meter cube is the same thing as 1 gram per cm cube. I need to mention that it's the same thing as 1 gram per cm cube. Did you get that?
Yeah.
So give me the density of water again. Let me zoom it in a bit. Give me the density of water again.
Density of water is mass.
No,
Sorry,
go to
1000.
the previous page.
I
Yeah, you
know
can see it.
1000.
Density of water is 1000 kilogram per meter cube or 1 gram per cm cube. Now I'm saying that because of the next thing I want to say very quickly, and that next thing is relative density. So I will just call it relative density, RD, relative density, RD. Relative density is simply density of substance, of object, all over density of water. Or you can say mass of substance, mass or weight of substance. So let's just say mass of substance all over mass of equal volume of water. So what I say relative density is? Density of object over density of water, or mass of substance over mass of equal volume of water. It's very easy. Look at this object we just found. What is its density?
3.3.
3.3 grams per cm cube. Let me zoom it in for you to see. The object we just found, the density is 3.3 grams per cm cube. What is the density of water?
1000.
Because that one is given in grams per cm cube. What's the density of water?
1
Gram per cm cube. Doesn't that tell you that if you want to convert gram per cm cube to kilogram per cm cube, you multiply by 1000? So can you put this one in kilogram per cm cube?
You multiply by 1000.
You multiply by 1000. If this 3.3 grams per cm cube can be written as
Let's just do it in
3.3 times 1000 to put it in kilograms per cm cube.
We can just do it in GMQ.
We will work, in fact, we will do it in GM cube. What you said is actually better because there's no need. I just wanted to bring up that point in kilogram per meter cube.
That's 3000.
If you wanted to put it in kilogram per meter, it would have been 3,300 kilogram per meter cube, isn't it?
Yeah.
So to change the density from gram per cm cube to kilogram per meter cube, you just multiply by 1000. Just an information you need to know. But you don't need all that. If they are in the same unit, you don't need to change anything. Let's look at this object we just calculated. Object A we just found. Object A, its density is what? We found its density to be 3.3 grams per cm cube, is it not?
Yeah.
And we know the density of water. We found the density of water to be what? We know the density of water to be what? 1 gram per cm cube. So what's the relative density of this object A?
3.3.
How did you get that?
Object A over water.
Exactly. Because relative density is density of object over density of water. So that means, let me just write that. I think after that we should be done with this. So it simply means relative density of object A is simply density of the object, which is 3.3 over density of water, which is 1. So that would be 3.3 over 1, 3.3 kilogram per meter, gram per meter cube if you like. I want to show you, I'm writing the unit for a reason. Gram per centimeter cube over the one for water, which is 1 grams per centimeter cube. Did you see that? And what does that give us?
3.3.
Simply 3.3. Does it have a unit? Can you see that this will cancel out? This will
Yeah.
cancel out. So relative density does not have a unit. No unit. It's relative because it's a ratio. It has no unit. Ratios don't need to have unit because the unit cancels the units cancel out. So the relative density of this thing is 3.3. So from relative density, you can find the density of the substance. Look at this formula. If, let me write it down here, relative density. If relative density is density of object over density of water, how do you find density of the object? Is it not just cross multiply? Let me write it down. Relative, go to the next page. If relative density is density of object over density of water, how can we now find density of the object if the relative density is given?
You cross multiply.
Density of object will simply be cross multiply this time this time this. Is it not?
Yeah.
Okay, because you can actually say this 1 over 1 if you like.
Yeah.
So density of object will now be what? Relative density times density of water. So a simple example, the relative density of object B, this is a simple example we can use to illustrate this. Object B is 5.5. Find its density. Let's go, everybody, quickly. The relative density of object B is 5.5. Find its density. What do we do?
Density.
What's the formula? See what we're going to
RD is equals to.
do. RD is given 5.5.
Yeah, I'm good to some.
Okay, so the density will just be answer. Density will be RD times density of water, isn't it?
Yeah.
What is its RD? 5.5, is it not? So we do 5.5. 5.5 times 1, that will give us 5.5 unit. This has to have a unit, gram per cm cube, or you can change it to kilogram per cm cube. What will it be? You know, you multiply by 1000, isn't it? So that will be 5500 kilogram per meter cube. If you're changing it to meter, kilogram per meter cube. Isn't that easy enough?
Yeah.
Okay. Okay, these are practice questions on what we've done so far. For instance, this one says the period of the vertical oscillation of a mass hanging from a spring is known to be constant. Now a student times a single oscillation with a stopwatch in 10 separate measurements. The stopwatch readings were, these are listed here. Now we say, what is the best value obtainable from these readings for the time of one oscillation? Now explain your answer, or explain how you arrive at your answer. So you state the best value and state how you arrived at your answer. That's a question here. Now it says, describe how using the same stopwatch the student can find the period of oscillation more accurately. Okay. As a question, don't forget, just a simple hint, period can be found by, of course, the period can be represented by T. Period T can be found by time taken for a particular number of oscillations all over that number of oscillations, you know. For instance, assuming we measured 30 seconds for 20 oscillations, the period will be 30 over 20. N stands for number of oscillations. T stands for the time taken. So that small letter t stands for the time taken. You know, so if it took 20 seconds to measure 30 oscillations, or what I actually said, if it took 30 seconds to make 20 oscillations, the period will be 30 over 20, which is 1.5 as the period, capital letter T. Now when you do this, of course you need to calculate or measure two different T's, like 2 or 3 different T's, and calculate an average just to make your reading more precise and reliable, more accurate and reliable. Some of this must be stated in your answers. The fact that you have to repeat readings and calculate an average to make it more accurate and also reliable. So for instance, you take 20 oscillations and 20 oscillations and measure the time for the first one, assuming you got 30 seconds. For the first 20 oscillations you did, and you've recorded 20 oscillations, you got 30 seconds. Then you take another 20 oscillations, assuming you got this time around 32 seconds. You need to find the average time. The first one you got 30 seconds. 30 seconds. The second one you got 32 seconds. So you need to find the average. 1 plus the other divided by 2. That's what you are eventually going to use as your average T, which of course will be 31. 30 plus 32 is 62, divided by 2 will give you 31. So the average is 31. And of course, when you divide it by 2, you have the average time. And you divide it by the number of oscillations, you have your period. So another question says, explain in terms of molecules why the density of oil is greater than that of air. And then this one says, define density. So these are practice questions. Then this one, you can read it out. You pause and read it, and then solve. This is the continuation of it. So practice questions on the topic we have some more. Let me zoom this out. Look at this one, number 4. That's number 4 here. There's also number 5. 5A. This is number 5. 5A. I think there's 5B on the other side. Let's look at 5B. That's the full 5B, B and C. You can pause and read it out and practice. This is C. B and C. Then there you have some more. You can find this. Pause and read it out and then practice. Look at this one, number 7. That's number 6. And number 7. Okay, we also have this. This continuation of number 7. And this number 8, I can zoom in a bit to reveal this better. Now this one, just a quick information, this says 80 kilonewton. Remember, kilo means times 1000, so this is about 80,000 newton. That's the weight. Okay, use a continuation of 8. I think this is 9, question number 9. We have question number 9 here. And I think finally we can look at this one, question number 10. Let me zoom it in properly. This should be a continuation of 9. Remember where 9 started from? This is where 9 started from. And this is the continuation of 9. Continuation of 9 is here. That's continuation of 9. And then of course you have 10. These are exam practice questions from past papers. This is a continuation of 10. These are selected topical questions on the topic discussed for the practice of the work done. So this should be fine.